discussed, rather we started talking about this idea of optimality, or the so-called Gauss-Markov theorem. So this result is stating that the least squares estimate has a sort of optimality property. And the main idea is that among all the unbiased estimators, all the linear unbiased estimators, this is the best one. So in short, you can say that the least squares estimate is the best linear unbiased estimator. Okay, so there is a formulation of this, which is stated more precisely here. We can go over them, but I just want to ask you guys to see if anyone had a chance to go over this on their own and whether they can help us go through this here.
Yeah, I got a chance to look at lecture 18, but I didn't get to the weighted least squares part.
Okay. And anyone else got a chance to look at this part? The Gauss-Markov?
I also had a chance to look at it a little bit.
Okay, okay. Anyone else? Kaylee and Jake so far? Okay, let's start with you guys. So what did you get? Maybe one of you who wants to go first. What did you get out of this result? Did you understand it? Was there anything unclear?
I think I understand it. So this is basically just saying that the beta hat would be the best least square estimate of beta, given that our conditions, our assumptions of the covariance is satisfied compared to any other general unbiased linear estimator.
Okay, yeah, so it's not the best least square. So the least squared estimate is just one. It's the best unbiased estimator among all the unbiased estimators, linear unbiased. So so there are two criteria here. Assuming that, yeah, assuming, as you mentioned, assuming that the covariance matrix of the noise is the way that we assume, so sigma squared IN, and that the noise is zero mean. So okay, so what does unbiased linear estimator mean, maybe? Do you recall what that means?
The unbiased part is just going to be that the expected value is equal to beta. And then the linear part means that for a B hat, it's equal to my for some matrix Y.
Okay, great. So if B is the candidate or competitor or competing estimator, then it's unbiased in the sense that, so we're working with or comparing with unbiased estimators in the sense that expectation of B hat would be beta. And it's linear in the sense that it can be written as a linear function or linear map applied to Y, which can be in general stated as a matrix M times Y. Okay, so that's great. So any estimator can be written like that. Can be compared with in this theorem. So beta hat. So is beta hat is it an unbiased linear estimator itself?
It is, because it can be written as like beta hat is equal to AY for some matrix A. So it's kind of like the same thing.
Okay, great. Yes. And then unbiasedness, is it unbiased?
Yeah, it's also unbiased. So the expectation of it is going to be just beta.
Okay, good. Yeah. So we proved this early on. So beta hat itself is in this class. So this is a class of estimators. So beta hat belongs to this class of estimators of beta. And then the Gauss-Markov says that within this class, beta hat is has a certain optimality property, assuming that the data is generated like this, the noise has zero mean, and the key is that the covariance is like that. So what is the optimality property? Maybe one of you guys, Jake or Kaylee. Maybe Jake, you want to go first? What
is the optimality property just that the beta hat is gonna, all the terms of like the beta j's are just gonna have smaller variance than the generalized, or not generalized, but other estimator of beta?
Right, okay, so that's one version of the result, is that the variance of all the entries, if you look at each entry, the corresponding variance is smaller than the variance of the competing, the corresponding coordinate of the competing estimator. So this holds for any j from 1 to d. I'm going to write d again as like p plus 1, whatever the dimension of beta hat and beta, sorry, and beta are. So let's say this is in RD. So this is great. So this shows that every coordinate has a smaller variance. This result is stated a little bit differently. So this is a little bit more. So did you sort of got that more generalized version? Is that? So what is this saying? Is this? So the way that's stated, this implies this, which is what you pointed out, but this result is a little bit more, I mean, has a little bit more in it than just the variances. So what is this saying?
This is saying that the overall covariance of B hat is going to be greater than, and is this because of the assumptions that it's linear and has the error has the sigma squared in, and the Kramer-Rao relation proves that this is the best overall estimator?
That's a great sort of point regarding the Kramer-Rao. So Kramer-Rao is not going to be effective in this case because we're not assuming any particular distribution for epsilon. So this result, the way that is stated, it is different than Kramer-Rao. I'll point out what the Kramer-Rao bound, where does it come in? But that's a great point. The reason why this is held is because of the proof. So that's the theorem. What I'm saying is that what does it mean? I mean, does it? So this is a matrix. This is another matrix. I'm saying this matrix is bigger than this matrix in a particular sense. So do you recall what this kind of wiggly inequality means? So what does this mean actually? What does it mean for a matrix to be bigger than the other matrix? It's not that obvious how to define that, right?
The difference would be positive.
Difference would be positive. So what does it mean for it to be positive?
So yeah, covariance of beta hat minus the covariance of, it's like the matrix that would give would be positive, semi-definite.
Okay, great. So that means that, this notation means, so this is exactly the same as this. And a matrix, when you write it like that, usually you mean that A is positive semi-definite. So this is a particular ordering on matrices. And that's exactly the meaning. So I'm going to write A is bigger than or equal to 0 in this fashion if A is positive semi-definite, and I'm going to write A is bigger than or equal to B if and only if the difference is positive semi-definite. That's one way of defining an order. So you could define things like pointwise, say one matrix is, we can say like A is bigger than or equal to 0 if every element is bigger than or equal to 0. We are not saying that. We're defining a little bit something which is a little bit more interesting than pointwise. In some applications, you care about pointwise positivity or non-negativity. This is equivalent to saying that this is PSD. Okay, so why does this imply this? Do you remember? So in order to show that, you have to say that if I have A is positive semi-definite, then it implies that the jth element is non-negative for all j. Because the variances are the diagonal elements, then this would follow. So this is what you have to show. I encourage you to use the definition. So follows from the definition. The definition. So if you recall, in the definition of positive semi-definiteness, so you have that this is non-negative for any u, for any vector u. And so you can choose u in a particular fashion such that you pick, so this is going to be equal to this. And as you vary j, you pick different u's. And so all the diagonal entries of a positive semi-definite matrix are non-negative. So this variance criteria follows. There is more that follows. So did you guys get a chance to, so why do we care about this? This has more information than this. Can you give me an example of an application of this where we can get more out of this than just the variance of each coordinate? So suppose I want to estimate beta 1 minus beta 2. What is a good estimate for this? It should be, like, everyone should know this.
Beta hat 1 minus beta hat 2.
Right, okay, so this is the plug-in estimator, which is a good estimator. Beta hat is at least the square. So you recall that this can be written as A beta hat, right? The corresponding competing estimator would be the plug-in estimator. So competing with A transpose B hat. This is also another estimator, which is like, this is going to be B hat 1 minus B hat 2. So if I have another estimate of beta, which is beta hat, if I want to estimate this for that estimator, this is a good estimate of this quantity. And then Gauss-Markov implies that the variance of A transpose B hat is also bigger than the variance of A transpose beta hat. Okay. So I encourage you to try to prove this using this result. So you can see this is more than just this. So any so the estimates that are based on linear combinations of the coordinates, basically any estimate of linear coordinates of beta, or any estimate of linear combinations of the coordinates of beta, will have the property that the variance of it is less than the corresponding variance for the other estimate. So any questions? So I see something in the chat. Pini says its eigenvalues are bigger. So is this, what is this related to? Is this related to a previous question, or? Not sure what that refers to. Okay, any questions? Try to show this exercise, that this follows from this result. Okay, so now no questions? All good? So I'm not going to prove this. There is a proof in there. I'm not sure if I go over the proof. You can go through the proof. If you have questions, let me know. It would be instructive. This is also part of the proof. What I'm gonna do is mention what the relation to the Kramer-Rao is. So this result is not assuming anything about the distribution of epsilon beyond the mean and the covariance. So we don't have the full distribution of y, and so we can't use the Kramer-Rao bound because Kramer-Rao bound requires the entire distribution. So if we assume normality, that's our second assumption, with this particular covariance matrix, then the Kramer-Rao idea would kick in. In fact, you can show that beta hat, the covariance of beta hat would be equal to the Fisher information in the inverse of the Fisher information matrix. So you have to go back to 200 or 100b to recall what the Fisher information is. In this case, there's a Fisher information matrix, and the covariance of beta hat is equal to the Fisher information inverse of the Fisher information matrix. And this is the Kramer-Rao bound. So the Kramer-Rao bound in that case tells you that covariance of beta hat for any unbiased estimator would be less than or equal to I theta inverse. And because the covariance of beta hat is equal to this Fisher information, that's the best possible. So this inequality would hold. So in the case of the Gaussian, this inequality basically shows that, so this inequality holds, and that's because this is equal to I theta inverse, or I beta inverse, and this is the smallest that this can be, this side. For any unbiased estimator, then you would conclude that beta hat is not only the best linear unbiased estimator, but it's the best unbiased estimator. So you can drop this. There is no other unbiased estimator, linear or nonlinear in that case, that can beat beta hat, which is a very strong statement. Okay, so that follows from the Kramer-Rao bound, because the Kramer-Rao bound, as I mentioned, if you do it in the multivariate case, Kramer-Rao bound says, let me do it there. Kramer-Rao bound says that covariance of B hat is bigger than or equal in that sense, bigger than or equal to I theta inverse. This is the inverse of the Fisher information matrix for any unbiased estimator. B hat of beta. And then in this case, we also have that covariance of beta hat is equal to I theta inverse. This you can verify. Maybe I'll assign this as a homework problem if you like. Covariance of beta hat is equal to this. And then if you compare that, you can see that from this it follows that the covariance of beta hat is bigger than or equal to the covariance of B hat is bigger than for any unbiased estimator, B hat. So then you can drop the linear qualifier. So in the Gaussian case, this is really the best unbiased estimator, period. Okay, does that make sense? So in general, it's the best linear unbiased estimator. So if you don't assume Gaussianity, there could be unbiased nonlinear estimators that beat it. But if you assume Gaussianity, that possibility is also ruled out. Okay. So why do we care about the variance being a smaller, or anyone can enlighten us about that? What is the significance of this result?
Does that just mean that the least squares estimator of beta, so beta hat is a better estimator than the other one because the variance is smaller.
Right, but why the variance being smaller intuitively means better?
Is it because like we're more confident about our estimation?
More confident. Okay, yeah, intuitively that's the case. The key is that because of unbiasedness, so just having a small variance in itself is not necessarily good. So you could have an estimator which, can you give me an estimator whose variance is 0 always? So you can always construct an estimator whose variance in itself is 0 always. Anyone can give an example of an estimator whose variance is always 0, no matter what the data is?
A constant?
Can you say that again?
A constant?
Yes, the constant, exactly. So if you just output like beta hat j is equal to 3, I don't care about the data, I just estimate beta hat j to be 3. I might be right, most likely I would be wrong, but the variance of a constant is 0. So this is 0. So what is wrong with this estimator?
It's not unbiased.
Yes, the bias in general would be very large. So the bias of this would be this minus beta j, which is 3 minus beta j. So the more you deviate, the more beta j deviates from 3, the larger the bias will be. So the key here is that if you have an estimator that's unbiased, then having a small variance makes sense. In that case, let's say if the variance is 0 and the bias is 0, so the bias is 0 means the expectation is equal to beta. If in that case the variance is 0, then your estimator would be exactly equal to beta, almost surely, with probability 1, which is really good. So this is saying that the center of the distribution is good. The center of this is the distribution of beta. The center is on the right thing. And then if the variance is smaller, it means I'm sharply concentrated. The smaller the variance gets, it means that the deviation, the randomness that I get around beta is smaller. So if you repeat the experiment multiple times, the estimator that has a smaller variance will have, like, with high probability would have, so your confidence intervals basically would have to have smaller length. And for a given level of probability, level of confidence, you need to like take you can take your confidence, like you can take the confidence intervals smaller. You can take the interval smaller, and it still contain the true parameter with the same probability. So that's just to remember. And there's something called the bias variance decomposition. Variance decomposition of the MSE. I should probably assign it as a homework problem at some point. You might have seen it, but the bias, so the MSE is a good criteria in general for measuring the performance, and the MSE can be decomposed into the bias squared plus the variance. And so you generally would like to reduce the MSE, and by reducing the bias and variance both, you would reduce the MSE, but there is a trade-off. You can't reduce both the bias and the variance at the same time. So you try to, like, one way is to try to make the bias 0, and then try to minimize the variance as much as possible. And so that gives you this idea of optimality, in the sense that you find the minimum variance subject to unbiased criteria. Okay, so that's just enough, I think, of this. I just wanted to make sure that you guys understand why this is important. So the least squares really has some nice statistical properties. So any questions? Okay, so let's go. So this connects to the idea of GLS. So let's see if anyone has looked at this idea. Jake said that, I think he did not.
Yeah, I looked at this one.
Oh, you looked at it. Okay. So
this is This is basically where our assumption of the covariance of epsilon is it's not standard. So instead of the identity matrix, it would be some known V, some known matrix V. And then we would transform our linear regression into a model that we have worked with before.
Okay, so, okay, great. So the idea is that we assumed that from the, like, early on, just the first few slides, when we talked about multiple linear regression, we made this assumption that the covariance of the noise vector is a multiple of the identity. So that's just saying that the covariance matrix has diagonal elements sigma squared and the rest is 0. So another way that the noise is the components of the noise are uncorrelated and each have variance sigma squared. And so the idea of general least squares is that this assumption might be violated in certain applications. And so we could try to generalize the problem and say that we're going to assume that the noise covariance is sigma squared, some unknown parameter times the structure, a known V, but V could be general. So this is a natural extension. Before this was the identity, known identity, but now it's a general matrix, positive semi-definite matrix. Has to be positive semi-definite because there's a covariance, but otherwise could be general. And then the question is that what can we do here? What should we do in this case? So there are some examples. I'll briefly mention. You can go over them from the lecture videos and then let me know if you have questions maybe next time. So an example is where each observation is obtained by averaging some independent measurements that you got, like maybe raw data was like this. In raw data, you might have like this assumption, but then you'd average out some of the entries. And so you did repeated measurements of a particular like subject, and then you average those out. Once you average, so what do you know about the variance of the average of independent variables? How does that scale? So if I have a bunch of IID random variables, suppose I have, sorry, suppose let's say Z1 up to ZM are independent, or IID, let's say. IID, and then variance of each one is sigma squared. So for all I from 1 to n. So what would be the variance of the average? If I average them, what will be the variance?
It would just be 1 over m times the variance of the zi's, correct? Or
yes,
sigma.
okay. Yeah, sigma
Okay.
squared by m. So as a statistician, this is something that you need to know. Perhaps the only thing that you need to know. That's why statistics sort of works. When you average a bunch of independent random variables, the variance goes down, and it goes down like sigma squared over n. In other words, the standard deviation goes down like sigma root over root n. Okay, so you get more accurate estimates. So let's say if these were unbiased estimator or something, this is still going to be unbiased because the expectation of this is going to be the same as the expectation of each one. The variance goes down. That's most like behind most of the things that you've learned so far in statistics, more or less. That would happen. So let's say each one of the observations that you get is something like this. And I sort of averaged for the ith guy, I averaged mi previous observations. Then my variance would be sigma squared over mi. And these could be different. So for one subject, I like repeated the measurements like twice. For the other one, I did it 10 times. So you'd expect that if the original variances were the same, you'd expect that the one that you did with 10 repetitions or replications, that would be more accurate. So in fact, that would be like exactly this result, and then your variance that would actually be proportional to sigma squared over mi. And then if you write down the covariance, so the new noise measurement noise, then it would have the structure sigma squared and then 1 over m1, 1 over m2, and so on. So this is a natural case where this something's called heteroskedastic. I mean, can't pronounce it, but you know probably what I mean. This was homoskedastic or something like that, and then this is heteroskedastic, if I'm pronouncing it correctly. So it's hard to pronounce, but the variances are different on the diagonal. Is it clear? That's one natural way. The other one is that you could have dependent observations. So this is an example. Again, you can read like there's some sort of a setup to make it believable. So this is like a sales quantity. These are like prices of certain things. And then the noise you can think of as, so the t here is time. So the observations are over time. And the noise from one time point to the other time point, you could assume that there is some correlation. Like this is related to some underlying economic forces, and the economy is not suddenly going to change. So like the change in the underlying economy is smooth. So perhaps if sort of this is like high at one time point, the next time probably is going to be high as well. If it's low, then it's going to be probably low as well the next time. So there is some correlation. I mean, it's reasonable to assume correlation for certain time series. This is an example of time series, and a simple model would be an autoregressive model. Okay, so the autoregressive model for the noise is a model in which you model the current time point as a function of the previous observation at the previous time point plus some independent noise. So this is independent. This is an independent IID sequence of Gaussians, but your new noise process is built by a fraction of the previous one plus this independent noise. And if this phi is less than 1, then you can show this is in time series analysis. You can show this can be a stable process. So there is a stationary process that satisfies this, and you could also argue for yourself that then the covariance matrix, or the covariance between epsilon t and epsilon t minus 1 would have this structure. So it would be sigma squared phi to the m. And because phi is between 0 and 1, this is getting smaller. So when you take it to the power, to an increasing power, this goes down. So this is like 1, this is smaller than 1, this is even smaller. This is like 0.1, this is like 0.1, this is 0.1. So it goes like to 0, but at a certain rate. So it's not exactly 0, but if you plot it, the matrix, this is going to be very, the values would be 1 here, and then slightly smaller, and then smaller and smaller, and so on. So usually you use colors, and the colors sort of go down towards 0. So this is a good exercise. I might assign it as a homework problem. We don't know. Maybe. But using this, assuming that this holds and the ZTs are Gaussian and independent, you can show that there is a correlation structure. And assuming that you know this phi, you know this entire structure, because this is just determined by phi, but still you don't know the underlying variance of the noise. So these type of models appear, the autoregressive model. The reason why it's called autoregressive, because this is like a regression where you regress the current value onto the previous value. So you're regressing it onto itself, hence autoregressive, okay? Just regress onto itself. So this is called AR1, and then they are AR. You could have AR2, which is like, there are 2 coefficients. You regress it into 2, the immediate past and 1 step further in the past. This is like multiple linear regression. So, and then you know how to fit these things. So if I give you if I just give you the noise process, you can estimate this phi by fitting a regression. So if you assume this to be the response, and this to be just the covariance. So you treat this as yt, you treat this as xt, and this is just a simple linear regression without any intercept, and then you can estimate. You get an estimate of phi hat, and you can do it for ARP in general. So don't be surprised if you see it in like homework or exams. It's just another example. If I like write it this, you can just treat this as yt, treat this as xt. This is just like a new noise. I'm not going to call it epsilon, but it's just an epsilon. This is going to be like sigma squared, or actually sigma. In any case, so if you have the noise, you can estimate this, and then from that point on, you can assume that we know this. We have done this, like say in the past, we know this phi, and so now I can assume it to be known. Now I'm going to measure some random variable for which this is acting as a noise process, and then so I know the new structure. I just don't know sigma squared. So this is an example where we have this v, but we don't know the sigma squared. And this structure is called the Toplitz's structure, and Toplitz means everything on the diagonals are the same. You can see everything on the diagonal is 1, everything immediately above and below the diagonal are phi, everything on the second diagonal is phi squared, and so on. This should be like yeah, it's hard to do. Like this is phi and then phi squared and so on. Okay, questions about this? You can also have spatial correlation. This is time correlation. So one time point is related to the next time point. The spatial correlation, you could have like a grid of points. Things that are spatially close could be like you have an observation here. It's related to observations on nearby sites. So you get like two-dimensional versions of correlation and so on. And you might know the nature of the correlation. Okay. Questions?
How would that look for like the spatial correlations in like, I guess, 3 dimensions?
I'm being a little bit vague here.
Okay.
It depends on how you model so I'm here. I'm assuming a very simple like grid structure. But then the question of how to model correlation is more tricky. So how do I assume that? So in the time case, I can do this autoregressive model. In the general case, it's not clear. Should I say that this is a linear combination of the other sides and then plus some noise? Sorry, give me a second. I'm going to come back. Okay, sorry. Yeah, so it's not obvious how to do how to exactly do this dependence. There is so suppose I assume that this is a linear combination. So I can assume that this side is a linear combination of the other guys plus some noise. Okay, but then this guy is also going to be a linear combination of this guy and this guy and this guy and the other guys and plus some noise. So you see there is some sort of a circular argument. So this is going to be a linear combination of these plus some independent noise. And also I want to assume that this guy is also a linear combination of these plus some independent noise and so on. And the question is that is there a distribution that satisfies all these constraints? And the answer is in general, yes. Let's say if you have Gaussians, depends on how you model noise. There are these things called Markov random fields. You can also think of it as in the 3 dimension, you have a grid, and every point would be like connected to like 8 other, actually 6 in this case. Let's say 1, 2, 3, 4, 5, 6. And then the observation at this point is a linear combination of the other ones plus some noise. Okay, if everything is Gaussian, let's say if you assume that these are Gaussians, and then the noise is also Gaussian, then you know that linear combinations of Gaussians are again Gaussian, so the entire distribution would be a Gaussian distribution. So there are the Gaussian Markov random fields that are easy to define. But it goes a little bit beyond the scope of this course. There are sort of examples of these are graphical models. You have some sort of tools, I mean, because you know the multivariate Gaussians, these are examples of the multivariate Gaussians, but they have more properties because of the way that they're defined. There are some interesting structure. So for example, if I define it like that, this is a linear combination of these plus some noise. This is a linear combination of the neighbors plus some noise. Then you could say perhaps this guy, is it independent of this or is it dependent of this? If I give you these, condition and these, whether these two are going to be independent, these questions can be asked and answered. Okay, so because of the way that this grid is defined, for example, in this case, the way I define it, if I condition on these variables, these are going to be independent. And this is one of the things that people would care about in graphical models. So there's a lot of story here, which we can get into, but in principle, it's possible to extend this. So this is saying that, let's say, even in the line, because there is some direction to time, here we are saying this is just a linear combination of the previous one, plus some noise. Even here, you can just have something which is bidirectional. So you can say this is a linear combination of these two plus some noise. This is a linear combination of these two plus some noise. This is the univariate Markov random field. But in time series, it's easier to define when you have this causality direction. That the direction of time is one way. So this is, I mean, this is defined properly. If you do it like that, there's a recursive equation that you have to worry about, whether you can sort of simultaneously satisfy all these conditions. And then the answer in general is yes. If you're interested, you can also look up the Gibbs distribution. There's a lot of these in probability. So what happens in general if I have like an infinite array and these distributions are, let's say, general, is there a distribution that satisfies all these local type conditions, and whether they exist or not depends on the structure of this, the geometry that you assume, the kind of grid that you assume, and so on. So there's a lot of story there. If you're interested, Google these things: Gaussian Markov random fields, Gibbs distributions, and then you'll have a lot to read about. Okay, that was good question.
Okay, thank you.
Yeah, so I would say this is like things beyond this course. Let's say very interesting topics, but beyond this course. I'd be happy to chat about them if you're interested. But just Google these and you'd have a lot to read about graphical models, Markov random fields, Gaussian Markovs, and Gibbs distributions, things like this. Okay, so let's get back to generalized least squares. So hopefully you're motivated enough now that this is a good assumption. There are cases where we have this set up. Now, okay, so how do we solve this, or how do we do this?
We have to transform the model in order to whiten the noise and get it back to sigma squared I.
Okay, yeah, so that's the idea. But why do we need to do that? Is there any, so let's say I do the least squares estimate. Is there anything wrong with this? This still works, right? So there's y, there's x, I can compute this. So what is the problem with this?
There might be better estimators, better nonlinear estimators.
better nonlinear estimators. How about linear estimators? Are there better? Are there better linear estimators or?
Yes, yes, I think so.
So is this going to be biased or unbiased? Is it biased? First, let's determine this. Is it biased or not?
It's unbiased.
So the answer is no, unbiased. Why?
Because the expectation of it is equal to beta.
Right. So if you take the expectation does not worry about the covariance. So the expectation cares about the expectation of y still is x beta. It's the same as before because we're still assuming that the expectation of epsilon is 0. So the same argument goes true, and the beta hat is still unbiased. So at least that's good news. If I change this assumption, I don't change the unbiasedness of beta hat. The only thing that changes is that because this is not true, then the Gauss Markov is not true. So we can't say that this new beta hat is the best unbiased linear estimator. We can't say that. And in fact, using the Gauss Markov, we can show that there is actually a best unbiased estimator. And so this is no longer best unbiased estimator. And the reason this is not best unbiased is that you can actually show what is the best unbiased linear estimator by doing the whitening as was pointed out. So the way to do it is that we transform this into a model in which the new noise vector has the original whitened, so this is white noise. This previous assumption. So if you multiply by v negative 1/2, so if you recall, this is a positive semi-definite matrix, so there is a square root. And if you assume that it's actually invertible, I'm going to assume that it's invertible, so this is in fact going to be strictly bigger than 0. So this is positive definite, not only positive semi-definite, positive definite. Then there is an inverse, so this will be invertible as well. Invertible as well. So this would be, the inverse would be v negative 1/2. I can multiply everything by v negative 1/2, and I can define, define new variables y tilde, x tilde, you see, epsilon tilde like this. So these are related to the original observation vector, design vector, and epsilon. And then going through the arguments that you now are familiar with, you can compute the covariance of this. And using the properties of this inverse, I encourage you to go through this, and you can show that the covariance matrix of this new vector is sigma squared identity. This is sometimes called white noise. So white noise is something, a vector or a process in which every coordinate is uncorrelated from every other coordinate. It's like white noise, and also the variances are the same. White noise is a little bit more general, so anything that's diagonal is white noise. But so this whitening procedure makes this diagonal and also the equal variance. Now, this is a new regression model. Y tilde is x tilde beta plus epsilon tilde. Now, in this model, we have the previous assumption. So the parameter is the same. The design has changed. The observations have changed. The noise has changed, but the parameter is the same. I can use my techniques to actually estimate the same object, which is beta, in this model. And if I form the least squares estimate in this model, beta hat least squares would be x tilde transpose x tilde inverse x tilde transpose y tilde. This is the least squares for this model. This is also called GLS, generalized least squares, in the original model. So in terms of the original x, x and y, if you do it, you'd get that if this is x transpose, I'm doing it here. So what you see is that this turns out to be x transpose v inverse x. So in terms of the original design, this is no longer, and y, no longer the least squares estimate. but it's so-called generalized least squares. Now, from the Gauss Markov theorem applied to this model, we know that this guy is the best linear unbiased estimator of data. And it's not hard to argue for yourself that this has to be, hence has to be the best linear unbiased estimator in the original model. Because the parameter is the same, you're estimating the same thing. This would have a smaller variance than this guy, for sure. So the variance or the covariance of beta hat and GLS will be less than or equal to the covariance of beta hat. And in fact, will be less than or equal to the covariance of any B hat where this is unbiased. So this is unbiased in the original model. This is unbiased and also minimum variance. So this is a better estimate. So this part, there's a little bit of argument to convince yourself that once you apply Gauss Markov, the Gauss Markov says that in this model, any estimator that's unbiased is beaten by this, but then you can see that any estimator in this model can be translated to an estimator in this model and vice versa. So the set of the class of unbiased linear estimators in this model is in one-to-one correspondence with the class of unbiased estimator in this model. It's very, it's just natural to consider that. So if you beat any estimator here, you basically beat any estimator in this model as well. So that's an application of Gauss Markov. So the same Gauss Markov theorem applied to this transform model shows you what the optimal estimator here is. Okay, and then you can compute the covariance. This is going to be unbiased, of course, and then the covariance would be just the covariance in the new model, which in terms of the previous model would look like this. Basically, everything that we did in terms of the inference, the T test, the T-based intervals, the F test, and so on, they are all relying on this assumption, okay? And because we have this assumption in the transform model, we can do everything in the transform model, and then you're going to be fine. And in terms of the original model, the formulas would be different. But once you understand that you're doing it in the transform model, the same formulas applied in terms of the transform design of the transform YTL. So for example, if you compute the residual, the residual in the transform model would be this, okay? And this guy, if you divide it by sigma squared, will have a chi-squared distribution. But this is not the residual. So if you think of the residual, this is an estimator in the original model. The way that you computed the residual usually is like this. This is not going to have. This does not have a chi-square distribution, okay? Because the way that we drive the chi-square, if you go back, it relies heavily on the assumption that the noise is like that, and the noise in the original model is not like this, and this is also not the least squares estimate in the original model, so this is not true. However, if you form the residual like this, then this is going to be true, and then you can see that this guy is in fact this is sometimes called the GLS, EGLS. So EGLS squared divided by sigma squared. This is the GLS residual. This is not going to be chi-squared, but if I form this guy, basically this divided by sigma squared is going to be chi-squared, and then your estimate of the unbiased estimator of the variance would be this guy, which is just this quantity divided by that. And so everything, if you do it in the transform domain, would be correct. And then you can translate it in terms of the original residuals, which is just this guy, and so on. Okay, so you should be able to do the proper T test, proper F test, and so on, as long as you're properly translating everything back. Okay. Sounds good? Questions? So there's a lot of like things that it goes here. So t-test, what like f-test, and so on. I'm assuming that you can fill in the details yourself. So everything sort of basically goes through just after this transformation. So try to work this out for yourself, and hopefully things will be all right. So usually in this case, you like beta hat, you can think of this as beta hat OLS. So you specify it as OLS relative to the GLS. So this is ordinary list of squares. And the ordinary list of squares in this case, as I mentioned, squares would be beaten by the GLS, and it's still unbiased, but the variance is higher than the variance of the GLS, and this is an implication of the Gauss Markov theorem. There is an optimization view, just like the OLS was. So beta hat OLS minimizes, if you recall, y minus x beta, or beta, let's say in RD. The beta hat GLS can be written as argmin of v minus 1/2 y minus exactly this. So what we have here, or beta in RD. So you add this extra v negative 1/2 inside the norm. And so this is the quantity that we are minimizing. So you can show that the solution of this is the GLS solution. And you can expand this. This would be a quadratic form like this. Compare with this guy for the OLS. Okay, so there's an optimization view. What else? Anything else that you guys remember from these? Questions, comments, clarification? Okay, if not, there is one last idea, which is weighted least squares. This is very much related to the GLS, and I just want to point this out. It's usually presented differently. So the GLS is motivated by saying that we have a different assumption on the covariance matrix, which is a very reasonable starting point. The weighted least squares is motivated by saying that I might, so this guy, think of the OLS, this can be written as argmin beta in RD, summation yi minus x I transpose beta squared, I from 1 to n. This is exactly the same thing. Here, xit is the itro of the design. This is x, the design matrix. So this is n by d. And so what we have here is this expansion. So you can see that you're basically computing the deviation of yi, the observation, ith observation from, this is the expected mean, or the expectation of yi under your model, and then squaring. In some applications, you might want to add some weight here and then minimize that objective function. So this is called the weighted least squares objective. The reason being that you might not, for a particular observation, you might not trust that observation much, so you don't want to weight that as much as the other one. So you would reduce the weight of that particular observation. Or for certain observations, you want to make those observations more prominent. So you trust them more, you want to make them, your regression, you want it to be close to those observations, closer than the other points. So that's a natural way to do it. So if you do write this down, you can expand it like this, where W is a diagonal matrix. And then if you compare this with this formula, you'll see that the objective is exactly like the GLS with W replacing V inverse. And because V is general in GLS, if I set V to be W inverse, so setting V equal W inverse in the GLS objective function, which is this guy, gives us the weighted least squares objective. Okay, so anything that we said about the GLS applies to weighted least squares with V being set to W inverse. So if you fit this, then you can compute the solution as the GLS, which is just this. Just you replace it with W here. Okay, so that would be the weighted least squares solution. The properties of the weighted least squares solution would depend on what you assume about the noise. So what we said, so the solution would be, this is going to be X transpose V X inverse V transpose, X transpose WY. Just think of this as W here, okay? And it just simplifies to these expressions. So this would be the expression, and this would be the covariance under the assumption that this is sigma squared I. If you're assuming that the covariance of the noise identity. So this is not here. You're not assuming that the covariance is there's any different assumption on this, but the covariance would be this, and this in that case is not going to be the weighted least squares is not going to be if the covariance is like this is going to be beaten by the OLS. Okay, so the reason why you do this is a different story. It's not because of the optimality issue. It's just for different reasons you do this. The properties of this depends on what you assume about the noise, and if the noise is like that, then the covariance is going to be like this, and so on. Right. So there are questions that you can answer here on your own. It's just I just want to point out the relation. So GLS is more interesting from a statistical perspective. This is interesting from a different perspective, but just wanted to point out. Okay. Questions? Comments? If not, let me bring up another set of slides. So, because you're going to use this in your homework problems. So we are almost done with chapter 5. So let's see. So this GLS was the last thing in chapter 4, and we covered a lot from chapter 5, like the comparison of treatments. There are other points in chapter 5. One was like the orthogonal design that we discussed. There is one specific point that I want to cover, and then chapter 5 is also almost everything in it is covered. The rest is just examples that you could look at. Chapter 5 is basically mostly examples. There are a couple of new ideas. One interesting idea here is the multicollinearity, which I wish I asked you guys to look at, but you perhaps have seen this from previous courses. Has anyone seen multicollinearity before? Anyone knows about multicollinearity?
Isn't it when the predictors have high covariances with each other?
When the predictors have high, okay, great. In this course, because we're mostly assuming the covariates to be non-random, the idea would be they're going to be the inner product is going to be high relative to the their norms. Like statistically, yes. So the sample covariance or the sample correlation would be high, or the sample covariance would be high relative to the sample variances. But you can, yeah, statistically, you can think of them as correlation. The idea is that if you have a regression model and then you have a design matrix, we assume that this design matrix is full rank, has full column rank, which means that the columns are linearly independent. Okay. In practice, it could be that they are linearly independent, but they are close to being linearly dependent. And this would happen, let's say, if let's say these two vectors are not in the same direction, but close to being in the same direction. So let's say if x1 is this and x2 is this, then they're exactly in the same direction, and the rank of this matrix would be reduced by 1. But if x1 is like that and x2 is like this, they're not exactly in the same direction, but they're almost in the same direction. And that would, mathematically, this would be acceptable. This would have like a rank 3. But the rank is not, it's just an integer. So it goes from 2 to 3. But it doesn't tell you how close you are to being 2. And this is really close to being 2. There are sort of more stable, they call numerical rank of a matrix that would be really high in this case. And so for numerical analysis, this is sometimes called ill condition. So a matrix that has full rank, but has the property that there are certain linear combinations of the columns that are close to being 0. That's called the ill condition matrix. One measure of it is like condition number, which is some sort of a numerical rank, if you want, numerical rank, or sometimes called a stable rank. This is like more of a these are more like continuous numbers. They vary continuously, and the closer you get to being rank deficient, the higher they go. So we want to avoid these cases. First, numerically, they're very unstable. So X transpose X inverse is very difficult to compute in that case, because this is getting close to being singular. Moreover, there is another issue from a statistical perspective. Anyone knows what the statistical problem will be if we are in this situation? So what would be wrong in terms of the estimates that we get for the betas?
I don't exactly remember the wording. Is it something like they're like inflated?
Okay, yes. So that's a good term. That's what the people would say. The variance of the coefficients would be inflated. Like a simply stated, the variances of the coefficients would be higher than you would expect based on the noise level. So there is part of the variance of beta that's due to the noise level, because there is noise here at level sigma squared. These can't have 0 variances. There's a natural noise level in the system, and you know that the covariance of, let's say, beta hat is sigma squared X transpose X inverse. But there's part of the variance that comes in because of the presence of these covariates, and the closer the covariates are to being low rank, this part that the variance shoots up. And this is not desirable. This is not due to inherent randomness in the model. It's just because of the way that your covariates interact with each other. And in those cases, in the worst case, to see what would happen is, in the worst case, let's say x1 is equal to 2x2. Okay, then what I would get is that this is beta 1. I can replace it with plus 2, 2 beta 1 plus beta 2 is equal to x2. So if I replace x1 with twice x2, the model reduces to this. So this is saying that beta 1 and beta 2 are not individually identifiable. It's just that this is identifiable. This is the identifiable parameter, because if I change beta 1 and beta 2 while this remains the same, the model is entirely the same. Okay, so if that's the case, I can't hope to estimate these parameters correctly. So if I estimate beta to be something, and then beta 2 to be something else, if I change beta 1 and beta 2, I still have the same number here, that would still be perfectly a valid parameter. So what this is saying is that these are not uniquely identifiable, or statistically they're not identifiable. And what it reflects is that the variance of these estimates would be infinite. If you try to estimate them, basically this is non-invertible, and you'd have infinite variance, which shows that these cannot be estimated correctly. When you're very close to being rank deficient, or have this property, I mean, this is like close, they are identifiable, but I can trade one off for the other one without changing. So this is not true in this case, but I can trade off a little bit of beta here for a little bit of beta 2, and the model still remains roughly the same. So if this is like 2x1 plus x2, I can probably reduce this to 1/2 x1 plus 1/2 x2, and the sum still is very close to the previous one. So that says that, again, betas are not that are not easy. There's uncertainty in them, and the uncertainty is not due to noise. It's due to the fact that x1 and x2 are correlated, or x1 and x2 are in the same direction. So you see, there is uncertainty here. I can reduce this to 1/2, and this reduce to 1/2, 1.5. And if 2x1 plus x2 is very close to this, everything goes through roughly the same, but the coefficients are really different. So this is changed to this, and this is changed to this. This is reflected actually in the variance of your estimator. So your variance of the estimator, in this case, beta 1 and beta 2 would be really high. And this is due to this multicollinearity. In these cases, it's advisable to drop one of these variables. And there are approaches to identify this issue, and how to resolve it usually is to get rid of some of these covariates. I'll come back and talk about this a little bit more. But please go through this because I didn't realize that next Monday is a holiday. So we have only 2 lectures left, and I have more to talk about. So next time I'm going to come back and briefly talk about the variance inflation factor from, let's say, the Wikipedia perspective. I'm going to talk about this. But there's a lot of stuff here that is also useful to look at. So I encourage you to go through this part, especially this example with the t-test and f-test. And this development here, this is the way that your book introduces variance inflation factor. So that the key here is variance inflation factor. The inflation was correct here. So that's the term that statisticians would use. And then I'm going to come back and discuss, this is more interesting, I would think. Then we'll move on to the next chapter on influence and leverage. Okay. Questions, comments? So go through the multicollinearity. I forgot which lecture it is, so I can take a look. But go through the multicollinearity from the previous lectures, and if you got a chance, look at the lecture before the last lecture, which is going to be about outliers and leverage and influences, things like this. Okay? Questions, comments? Okay, thank you guys for being here. Sorry that we went over